This is the fourth module of the course. The lessons will cover various network tools that you will find useful as a security professional. We will concentrate on open source tools, though the principles behind them are the same as commercial tools. In fact, there are some excellent open source tools that are commonly used by security administrators and professionals. This module consists of 4 short lessons. The first lesson will consist of a quick review of TCP IP. The second lesson discusses firewalls, their purpose, common settings, and alerts. The third lesson has us taking a similar look at intrusion detection and prevention systems. The last lesson will consist of a look at a number of common useful network tools. Then, as in previous modules, we will also include knowledge checks and a list of references or resources. If you recall, the concept of encapsulation is important for both the 7-layer OSI model as well as TCP IP. We used an analogy to describe this process. The analogy was to compare network encapsulation with a letter mailed through the post office. We put the letter inside of an envelope and put an address on the envelope to indicate where the letter should go. To send something in TCP IP, we need to do something similar. We will put the data packet inside of a digital envelope with an address as to where it should go. We add a header to the data, and in some cases possibly a footer, which are designed to tell what to do with this data, and then we bundle these together. This can then be passed as a single entity to the next lower layer, which will handle this entire bundle as its own data. It can then add another header and possibly another footer as well. When a system receives information from another system, the process is reversed, with a layer receiving information from the layer beneath it. Each layer will strip off the header and footer in order to determine where to send it to in the layer above. The TCP IP protocol suite consists of a number of different protocols seen throughout the 4 layers of the model as shown here. In this diagram, the lower 3 layers correlate with the lower layers of the OSI model very closely. The top 3 layers of the OSI model all fit into the application layer of the TCP IP protocol suite. For the most part, the protocols shown here and other protocols not shown here follow the encapsulation concept and communicate only with the layer directly above and below it. The ICMP, or Internet Control Message Protocol, embeds its header inside of an IP packet, for example, and the complete packet is then handled as an IP packet when sent across the Internet. ICMP is considered a support protocol and is not used to transport data between systems and end users. At the application layer, the protocols are found that handle common applications users utilize. These include the Hypertext Transfer Protocol, which we all know as HTTP. It handles our web traffic. SMTP, or the Simple Mail Transfer Protocol, is used for sending and receiving emails. At the transport layer, we have 2 workhorses of the TCP IP protocol suite. The first is the Transmission Control Protocol, or TCP, which is a connection-oriented protocol, and the User Datagram Protocol, or UDP, which is a connectionless protocol used for loss-tolerating and low-latency applications. At the Internet layer, we can find ICMP, which we already mentioned, and IP, which is the Internet Protocol. This is another workhorse protocol in the TCP IP suite. It is important for sending datagrams across the Internet. The link layer is the lowest layer in the TCP IP suite of protocols. It is here we will find a number of protocols used to connect between adjacent nodes in a network segment. This diagram depicts what occurs when sending a packet across the Internet. Notice at the top 2 layers, the transmission can be viewed as a direct connection between the two endpoints. At these layers, the protocols are not responsible for the routing of the packets through the many systems that make up the Internet. They are only concerned with the two endpoints. At the bottom two layers, the object is to route the packets to their correct destination. Routing decisions are made as to where to send the packets for the next leg of their journey. This may include through LANs, as indicated here, as well as across the wide area networks. Probably several of these before arriving at the local network connected to the destination system. At the destination endpoint, the packet is received and the system has to decide how to handle it. It will look at the headers to decide where it needs to go at the network layer. This might include being handled by the ARP or ARP, or Address Resolution Protocol, which helps to determine the correct media access control address on the network given a specific IP address. It could also mean being handled by the IP protocol, which will determine if the IP address of the destination matches this system's IP address. It then needs to determine where to send it at the transport layer. This might mean being handled by TCP, the connection-oriented protocol, or UDP, which is a connectionless protocol, or it could be handled by ICMP, which we mentioned before can also be viewed as being at the same level as the IP protocol. If it was shuffled through TCP IP, it could then go to one of several services such as HTTP, SMTP, or FTP, the file transfer protocol. If it was shuffled through UDP, it might then be handled by SNMP, the Simple Network Management Protocol, or DHCP, the Dynamic Host Configuration Protocol, or by DNS, the Domain Name System. Finally, if ICMP was handling the packet, then it might be handled by an application such as Ping or Traceroute. What we are most familiar with on the Internet is to be able to gain access to a website by using its name, such as somesite.com. These names are used because they are easy for humans to remember, but what the network uses is an IP address that is included in the IP protocol. In this protocol, the source IP address is placed to show where the packet is coming from, and the destination IP address, which is placed to indicate where it is to be sent. One layer above this, we see a source and destination port, which specifies what application or service was the source and what application or service is the destination. The IP address is contained in a 32-bit location and is normally written as 4 decimal numbers such as 129.105.120.47. Each of these dotted decimal numbers is determined by splitting the 32-bit address into 4 8-bit parts, each represented by its decimal equivalent. Keeping track of what name is associated with its actual IP address is accomplished using the Domain Name System, or DNS, and will be discussed later. The Internet does not just consist of a bunch of systems which have had an address assigned to them in a haphazard manner. Instead, the address space is split into 4 network classes labeled Class A through Class D. An organization may be assigned an address space in one of these classes, which will give them a specific number of addresses they can then use to assign to their own systems. For example, a Class A network address will use the first 8 bits as its network address, and the remaining 24 bits will be used to specify a particular host. There are only 127 Class A networks, each of which can have over 16.7 million hosts. Compare this with the Class C class, of which there are over 2 million networks, each with 254 hosts. A more recent development, CIDR, which stands for Classless Interdomain Routing, is being offered up as a replacement for the class system, It promises to offer a more efficient distribution of IP addresses. A couple examples of the type of notation you may see being used are shown on this slide. There have been several versions of the Internet Protocol. Remember that IP handles the source and destination address. When the format for the protocol was first created, enough bits were allocated for these addresses to handle over 4 billion Internet addresses. Unfortunately, since that time, the Internet has exploded in size, and it became obvious that unless something was done, the Internet would run out of addresses before too long. One method devised to address this issue was network address translation, which we will talk about a bit more later. Another approach to handle the situation was to expand the size of the address space, which is exactly what was done in IP version 6. The address in this version expanded the address space from 32 to 128 bits. This results in a much larger number of possible addresses, more than 3.4 times 10 to the 38th, in fact. IPv6 also has some enhanced security features. When we as humans want to access a website, we type into our chosen browser the name of the website, such as whitehouse.gov, microsoft.com, www.nintendo.com, or the three examples shown on this slide. Recall our discussion of the TCP IP protocol suite and the IP protocol. The names we remember our sites by are not what the protocol needs. It requires the specific IP address for the site. The question then is, how does a name humans use get translated to the IP address the network needs? The answer to this is the Domain Name System, or DNS. DNS will determine the IP address for a given web domain name. This translation from a name to a number is akin to the use of a telephone book, where we have an individual's name and we want to find their telephone number so we can call them. Because of the similarity of the two, DNS is sometimes referred to as the phone book for the Internet. Previously, we mentioned TCP and UDP. Let's take a look at them in a little more detail. TCP is the Transmission Control Protocol. UDP is the User Datagram Protocol. TCP is connection-oriented, which is what enables the guaranteed delivery of packets. A connection needs to be set up before transmission begins, and the packets sent are numbered and kept track of. This is what makes transmission slower, but will also mean that the lost packets can be retransmitted. Earlier, we also mentioned that UDP was connectionless. This means that it is going to be faster than TCP, but that it also does not guarantee delivery. Because of this, lost packets will not be retransmitted. All of this makes UDP a simpler protocol. In general, UDP is used for services such as video teleconferencing, where a lost packet will not have a large impact. TCP is used for services such as email, web traffic, and file transfers, where ensuring you do receive all packets is more important. We stated that the TCP protocol is a connection-oriented protocol. This differs from UDP, which is connectionless and is sometimes referred to as a fire and forget protocol. This means that when UDP sends a packet, it is not worried about whether it was received by the destination correctly. The packet is simply sent along and forgotten by the sender. TCP, on the other hand, has processes to ensure that packets are received and then reassembled in the correct order without losing any. To set up the connection between two systems, TCP first uses what is known as the TCP three-way handshake. The TCP three-way handshake starts the connection between two systems. It sets up several sequence numbers that will be used during the transmission to ensure packets are received in the correct order. It does this with a series of synchronization or SYN or SYN packets and acknowledgement or ACK or ACK packets. The entire process works as follows. The system wanting to set up the connection sends a SYN packet and includes a number it selects to start the sequence. The receiving system sends back a SYN ACK packet with the initial sequence number incremented by 1 and a new synchronization number for the second system. The initial system then responds with a final ACK with the sequence number incremented by 1. In essence, what has occurred is the first system tells the second, "Hey, I want to talk to you." The second says, "Okay, I'm ready, let's talk." The first system then says, "Wonderful, we can now begin," and the communication can commence. A couple of final comments. When the communication is to be closed, the systems exchange a pair of FIN or FIN and ACK packets to say, "I'm finished." Additionally, there is a limited number of TCP connections that can occur at a given time. This becomes important in a specific type of attack known as SYN flooding. One final comment for this lesson. The article, Top 20 Open Source Tools Every Blue Teamer Should Have from Blue Team's Academy, is a great resource to check to see what tools you might want to get to know as a cybersecurity professional. Blue Team Academy also has some great free training you can check out. This ends the first part of Module 4. Time to do a quick knowledge check. What is the purpose of CIDR in IP addressing? Make it harder to spoof IP addresses, thus improving security. Increase the number of IPv4 addresses until everybody is ready for IPv6. Create a more efficient scheme for distribution of IP addresses. Or create a simple conversion method to translate IPv4 to IPv6 addresses. CIDR is the classless interdomain routing scheme, and it is designed to create a more efficient scheme for distribution of IP addresses. Which one of the following is not true of UDP? It is generally quicker than TCP. It is simpler. Its delivery is not guaranteed. Or it is connection-oriented. UDP is connectionless, not connection-oriented. Which of the following is the sequence we expect to see with a TCP three-way handshake? SYN, ACK, reset, SYN, SYN-ACK, ACK, SYN, ACK, SYN, or SYN, SYN-ACK, reset. The sequence should be SYN, SYN-ACK, ACK. This concludes Lesson 1 of Module 4.